Okay, we're talking polygons today. And before we can really talk about a whole bunch of different types of polygons, we need to define what a polygon is. Um, a polygon is a simple closed figure made up of line segments. Now, I've told you this before. In math, we're not allowed to use a word until we've defined that word. So I kind of need to take a little step back here and make sure we define simple and closed, so then we can sort of focus in on what our polygons are. A figure is simple if it does not intersect itself. If you're thinking, well, that's all well and good, but I don't know what that means. Well, here's an example of a simple figure. A simple figure could be like that. It does not intersect itself. Nowhere does that figure intersect itself. Perfectly reasonable for you to be thinking, okay, well, what's a figure that's not simple look like then? Great question if you're having it. Something that's not simple might look like this. And you can see right here, it has intersected itself. And so this blue shape over here is simple because it does not intersect itself. This red shape over here is not simple because it does intersect itself. As we go through any of these terms and definitions, please don't hesitate to let me know if you have questions. Like here, I tried to anticipate a couple, and I'll continue to try to do that. But if you have things that come up that you want to ask about, please make sure you do that. The next word we need to give a definition to is closed. And a closed figure starts and ends at the same point. And an example of that might be, notice we started right here, and when I draw it, I end at the same place. Now, it doesn't have to be the upper left. I could have drawn this same shape by starting out down here, and I draw the figure, and I start and I end at the same point. And a figure that's not closed, well, we start it, but then we don't end at the same point. We end over here, and it never really closes. It never finishes the picture, if you want to think of it that way. But here we have a closed figure that starts and ends at the same point, and over here we have a figure that is not closed. Simple and closed are important words for us, but really we were pointing towards the idea of a polygon. And a polygon is a simple, closed figure made of line segments. So to be a polygon, it has to be simple, meaning it does not intersect itself. It has to be closed, meaning it starts and ends at the same point. We're going to look at a lot of polygons today, so you'll see plenty of examples of that. One thing that has to be brought up, though, it's kind of important for us to address this one, is a circle. That's not a great one. Let me do another. There we go. A circle. And you look at that and you think, well, it's simple. It doesn't intersect itself. It's closed. It starts and ends at the same point. The reason that circle is not a polygon is because it's not made of line segments. It's just a curve. And so anytime we have a polygon, it's going to be made up of line segments. Like you can see here, we have a closed, simple figure made up of line segments. That would be a polygon. It's the only polygon we have on this page right now. Are there any questions about any of those definitions and what a polygon is and is not? Like I said, we'll see lots of examples of polygons as we go through class today, and that can help too. Here's some common polygons. A lot of these you probably already know the names for. Some of them you may not, and that's okay. Here's some common polygons, and basically the names are related to the number of sides. So these polygons have names that are related to the number of sides. So probably pretty familiar for most of you is the idea of a triangle that has 3 sides. And this is just an example of a triangle. Certainly, excuse me, a triangle could look different than that, but that's an example of a triangle. And then quadrilateral, the prefix quad sort of indicates that, you know what, this is going to be about 4. And that's true. Quadrilaterals have 4 sides, and quadrilaterals can look different from this, but that happens to be in one example of a quadrilateral. And then we get to 5 sides, and that's called a pentagon. 6 sides is a hexagon. 8 sides is an octagon. One you might not know is that 9 sides is a nonagon, and another one you might not know is that 10 sides is a decagon. And while there are some names for figures bigger than this, really, once we get beyond 10, we kind of lose our creativity here. Like if we had a 13-sided figure, we'd just call it a 13gon. A 19-sided figure would just be a 19gon. And so, once we get beyond 10, our naming becomes a lot more sort of rudimentary instead of using prefixes to go with those names. I will say that without a doubt, the most important polygons for us are going to be triangles and quadrilaterals. And we're going to spend the vast majority of our time on those. And you'll see that as we go through class today. A couple more words that we need to make sure we're comfortable with the definitions of: concave and convex. Start out sort of a formal way to distinguish between the two, because every figure is either concave or convex. It's one or the other. So this is an either or type of situation. When we draw a figure, it's either concave or convex. And formally, we would say that a polygon is convex if the line segment containing any 2 points lies entirely within the polygon. If your head's swimming on that one a little bit, I totally understand. Formally, it's convex, which you can see from this label are the ones on top, is if the line segment containing any 2 points lies entirely within the polygon. So I have a point here, I have a point here. My pen doesn't want to behave. Give me just a minute. Okay, hopefully we're fixed up. I have a point in that top left, I have a point in the bottom right. The line segment containing those 2 points would be entirely inside or within the polygon. And that's going to be true no matter what. Here, line segment containing 2 points is within the polygon. Line segment containing 2 points is within the polygon, and so on. And you're going to see that that's true of all of those convex polygons. Concave, that might not be the case. If we look down at the bottom, we can see here in this first shape, these 2 points are on the figure, and if I connect them, it's not within the polygon. It goes outside the polygon, and that's going to be true here, and it's going to be true here, and it's going to be true here. And so if I can connect those points and go outside of the figure, then I know that it's concave. Informally, and this is something that works really good with kids, I think. Informally, it's concave if it has at least one of the sides caved in. And you can kind of look like, yeah, well, this would have been a triangle, but you know what? This side got caved in. And here, this got caved in, and this got caved in, and this has 2 sides caved in. And so whichever way makes the most sense for you is how you can approach the idea of concave versus convex and just sort of identifying whether a figure is concave or convex. And the formal definition and trying it out by trying to connect points and see if you go outside the figure, or more informally, because that's going to work too. If it has a side caved in, when you go to connect points, it's the cave where that line that goes outside the figure is going to be. And so that's our distinction between concave and convex. One thing I will say about all of the figures on this page, every single one of these is a polygon. Notice, they are simple. They don't intersect themselves. They are closed. They start and end at the same point. So they're all polygons. Some of them are concave, some of them are convex. Okay, I mentioned that we were going to look at quadrilaterals and triangles. This was going to be sort of the bulk of our study of polygons. And we're going to start with quadrilaterals. There are 5 different quadrilaterals here on this page, and we're going to go through each one of them and sort of talk about their properties and what makes them that thing. Well, first we'll start out with a trapezoid. Well, actually, the first thing I want to start out with is these are quadrilaterals, meaning they all have 4 sides. If you look at each of these, they all have 4 sides. They're all polygons. They are simple, closed figures made up of line segments. So those are all polygons. They all have 4 sides. That's what makes them all quadrilaterals. Now, within the topic of quadrilaterals, we have some properties that go along with each name, each type of shape. And the first one we're going to look at here is the trapezoid. In a trapezoid, at least one pair of opposite sides is parallel. So here, the top and the bottom are parallel. And that's enough to make this a trapezoid. Those 2 lines never intersect. If I were to extend them forever, the top and bottom are parallel. Now, if you look at this trapezoid, you can see that the left side and the right side are not parallel. Well, as far as a trapezoid goes, it just needs at least one pair of opposite sides, opposite meaning top and bottom are opposite, left and right are opposite. So one of those pairs needs to be parallel for us to call this a trapezoid. And sure enough, that particular shape has one pair of parallel sides that are parallel, so it's a trapezoid. Going forward, our next shape is the parallelogram. To be a parallelogram, both pairs of opposite sides have to be parallel. So what that means is this pair, top and bottom, have to be parallel, and also left and right have to be parallel. So in order to be a parallelogram, you have to have both pairs of opposite sides be parallel. One thing I want to say with a lot of these definitions, and we're going to look at some practice before too long, but they set themselves up for really good true-false questions. And at the surface, true-false is like, awesome, it's going to be true-false. This will be no trouble at all. I'll just sort of give you a heads up. Sometimes true-false questions can be pretty challenging, and this is one of those areas. So here's my first true-false question to you, and I kind of hope I don't wreck something that I have in mind for later on. I don't think so. Okay, good. My first true-false question to you is true or false that green parallelogram right there, that is a trapezoid. I'm gonna go ahead and set up a poll for this. I didn't intend on it, but I'm gonna set up a poll for that. True or false, that parallelogram is a trapezoid. So give me a minute to set up a poll. And like I said, I don't think all true false questions are easy. I think sometimes they can be darn challenging. And so when it comes to questions like this, you've really got to think through, what is the definition of a trapezoid? What is the definition of a parallelogram? And that's how we'll decide whether or not this is true or false. And I don't need you to overthink this. We're just talking about it for right now. So, this is a new idea, and the idea that the relationships between different polygons are going to be true false questions could be a new idea for you. So, with that in mind, just kind of give this one a shot. All right, let's take a look and see how we did on this one. Okay, pretty good. We've got strong agreement there. That's excellent because I don't think this is an easy question. All right, so let's examine this a little bit here. So this parallelogram that I'm working on here has both pairs of opposite sides are parallel. For it to be a trapezoid, it needs at least one pair of opposite sides to be parallel. So I guess really when we're saying, is this a trapezoid? What we're saying is, does it have at least one pair of opposite sides that are parallel? And sure, top and bottom are parallel. That's good enough to make it a trapezoid. The fact that it happens to have both pairs of opposite sides parallels that's nice. That makes it a parallelogram, but it is a trapezoid. So that would be a true that it is a trapezoid. All right, some more quadrilaterals that you're probably pretty familiar with. A rectangle. In a rectangle, it's a quadrilateral. All angles measure 90 degrees. And so we have four 90-degree angles in our rectangle. That's what makes it a rectangle. It's a quadrilateral where all the angles measure 90 degrees. Now, I want you to notice, and I won't dwell on this, but I want you to notice that top and bottom, as well as left and right, are parallel. So that rectangle, it's a parallelogram. And it has at least one pair of parallel sides, so it's also a trapezoid. There's sort of a hierarchy here where, a rectangle fits into a bunch of different categories. Not only is it a rectangle, but it's also a parallelogram, and it's also a trapezoid. If you have questions on that as I say it, please make sure you ask. The next one is a rhombus. And a rhombus is a quadrilateral, meaning a four-sided polygon, where all the sides are equal in length. The way that we denote that on a figure is we just put a little hash mark here like this to show that they're the same as each other. That one little hash mark indicates that they're the same as each other. And so all sides are equal in length. Now, if you happen to notice by looking at that rhombus that, hey, top and bottom are parallel, what's going on with my pen? Top and bottom are parallel, left and right are parallel. So it happens to be a parallelogram also. And because it has at least one pair of opposite sides parallel, it's a trapezoid also. So they fit into more than one category a lot of times. Now we get to the square at the bottom, and you're probably pretty comfortable with the idea of a square. Square is very specific. All sides are equal in length, and all angles are 90 degrees. So for a square, all the sides are 90 degrees. And all the sides have the same length. And that's what makes it a square. And you can see that square is also a parallelogram. It's also a trapezoid. Finally, a kite. We don't always talk about kites. They don't come up that often in very many courses, actually. It's kind of why it's at the bottom down there. In a kite, two pairs of adjacent sides are congruent. And adjacent, just like with angles, sides that are adjacent are next to each other. So two pairs of adjacent sides are congruent. So a kite is going to look exactly like you would think something called a kite would look. And we said that two pairs of adjacent sides are congruent. So in this kite, what we have here is these two sides are congruent to each other, and then these two sides down here are congruent to each other. And the way we indicate that, okay, the two top ones are the same is by using one hash mark. And the way that we indicate the bottom ones are the same is with two hash marks. So if we just have our kite like this, and we want to say these two are the same as each other, and these two are the same as each other. And then make sure we're meeting the conditions of what a kite actually is. Two pairs of adjacent sides are congruent. Well, here's one pair of adjacent sides that are congruent. Here's another pair of adjacent sides that are congruent. And that's what makes this a kite. Now you'll notice that kite doesn't necessarily have opposite sides parallel. So we have to keep that in mind when we talk about a kite. Are there any questions on these definitions before we look at a couple of true-false questions that we'll just sort of think about first and sort of get the idea of true-false questions sort of in hand before we keep going forward? All right. Relationships between quadrilaterals. This is how we get to our true-false questions. And the first question says, all rectangles are parallelograms. And the idea here is we're after true or false. Okay, all rectangles are parallelograms. So I got to talk to you a little bit about true, false, just sort of in general, and the idea of all. When we say all in math, we mean absolutely no exceptions. So same thing with the word every, means every single one, no exceptions. So it's a little different than conversational walk-around language. If we were to say, it's sunny all the time in Las Vegas, you could get away with that. That's something that you could say. But you know what? If there was one day back on January 3rd when it was raining, then that statement is false. All we need to show something false is one counterexample. All you need to show something false is one counterexample. So if I can come up with one counterexample, then I can say this is false. And that's how we're going to approach questions like this. We're going to approach it from a standpoint of, can I find a counterexample? Because if I can, then I can assert that this is false, and I can be sure of it. All right, let's see if I can find one here. All rectangles are parallelograms. So what I'm going to try to do is I'm going to try to draw a rectangle that is not a parallelogram, because if I can, then that is my counterexample. If I can draw a rectangle that's not a parallelogram, that's my counterexample. So let's see here. I'm going to draw a rectangle. Okay, well, poorly drawn, but parallelogram means both pairs of opposite sides are parallel. Yeah, that rectangle is a parallelogram, so that's no good as a counterexample. All right, well, what if I draw my rectangle this way? Well, if I look at that, both pairs of opposite sides are parallel. You know what? As I do the work to try to find a counterexample, I might convince myself that this is true. You're not going to have to do a proof. And if you remember back to high school geometry where you had those two-column proofs where you put a statement over here and a reason over here, we're not going to do any of that. And you're not going to have to prove that this is a true statement. But in your work toward looking for a counterexample, you might convince yourself, you know what? Every rectangle is going to have both pairs of opposite sides parallel. So every rectangle is going to be a parallelogram. So the statement, all rectangles are parallelograms, well, that's going to be true. And that's sort of our process for answering questions like these. We see if we can find a counterexample. If we can, great, we call it false. In the process of looking for that counterexample, we might convince ourselves, you know what, that statement's true. Let's look at the one at the bottom. All rhombuses are squares. Okay, all rhombuses are squares. So I'm going to try to draw a rhombus that's not a square. I'm looking for a counterexample. So if I draw a rhombus that looks like this, all sides are equal. Well, that's not a square because it doesn't have right angles. So I found my counter. All rhombuses are squares. No, they're not, because I can prove it right here. So that statement is false. I found my counterexample, so I can say that it's false. All right. Do you have questions about either of those or the process before I have you try a couple? Fantastic. Here goes. So I'm going to set up a poll for this. Each question is true or false. And so you want true or false for the one on top, true or false for the one on bottom. Every trapezoid is a parallelogram. All squares are rhombuses. And if you're wondering how you're going to answer two questions at once, you'll see when I post the poll. So the answer on the left goes with the top question, and the answer on the bottom goes, or the answer on the right goes with the bottom question. And so, so true or false for each, and then you find the one that corresponds with what you think is correct here. And these are the types of questions that you can expect to see on a quiz or an exam related to properties of quadrilaterals. If you're thinking, okay, these are a little bit challenging, then I'm guessing you're not alone. I do think that these are not just sort of simple, oh, obviously that's true. They definitely take a little bit of thought. They take a little bit of work. I'm confident you can do well with them. You just have to make sure that you're comfortable with the definitions of all those quadrilaterals. And then once you know that, then you sort of approach these from a standpoint of, all right, can I find a counterexample or not? And that's how we'll decide true or false. We'll go another 30 seconds, and then we'll talk about this one. Or I guess these two. Let's see where we are. Okay, strong agreement, but spread all over. That makes for interesting discussion. Okay, very good. So we're going to go back and take a look at these two. If you have questions you want to ask, or you're not sure of the thought process, please make sure you ask about it. The first one says, every trapezoid is a parallelogram. Remember what my approach here is I am looking for a counterexample, and all I need is one. If I find one counterexample, then this is false. So if I draw this trapezoid, and a trapezoid has at least one pair of opposite sides parallel. So this is a trapezoid. I've got top and bottom are parallel. That qualifies as a trapezoid. At least one side of opposite sides are parallel. And this says every trapezoid is a parallelogram. Every one, all of them. Well, I just drew one right here. And this has top and bottom parallel, but it does not have left and right parallel. So right here, I have a trapezoid that is not a parallelogram. So that statement that I was given right out of the gate must be false. Is it possible to draw a trapezoid that is a parallelogram? Sure. But that's not what this question said. It didn't say there exists at least one trapezoid that is a parallelogram. That's a way more thick language question that we're not going to deal with. Every trapezoid is a parallelogram. Well, here's one that's not. So it's false, and I'm sure of it. Now we'll go to the one at the bottom. All squares are rhombuses. Okay, so I'm going to look for a counterexample. I'm going to draw myself a square, and I want it to not be a rhombus, because if it's not a rhombus, then I can say false. Well, this square has all four sides the same. Oh, well, that makes it a rhombus. All right, well, what if I draw a really big square? Well, by definition, a square has all four sides the same. That's a rhombus. You know what? Every square I draw has to have all four sides the same length. And if it has to have all four sides the same length, then it has to be a rhombus. So all squares are rhombuses. You know what? That's true. Every square I draw is going to be a rhombus. One thing I want to point out to you, if you're a little bit twisted up about this, on the last one we said all rhombuses are squares, and that was false. And then here we said all squares are rhombuses, and that was true. What's going on here? Well, let me put it this way, because this is one that helps me with these. It really depends which one, what order those go in when we say it. Because I could say to you, all Dalmatians are dogs, and that would be true. But if I said all dogs are Dalmatians, that would be false. And so which word is in which spot definitely makes a difference. And that's why we wound up with this statement false and this statement true, even though they look very similar to each other. Before we go on to triangles, I just want to give you a chance to ask anything you want to about the quadrilaterals and those relationships that we've talked about so far. Are there any questions about quadrilaterals? Okay, we must be doing great. Both polls went pretty good. So I feel pretty good about that. In a similar way that there are different characteristics that go with different quadrilaterals, there are different characteristics that go with different triangles. And here's a bunch of different types of triangles that we're going to talk about. The first triangle that we're going to talk about is an equilateral triangle. In an equilateral triangle, all sides are equal and all angles are equal. So all three sides are equal and all three angles are equal. You don't have to remember this, but if you do, what is the sum of the angles in a triangle? Anybody remember? If you add up all the angles inside a triangle, what do you get? If you don't remember, it's okay. We're certainly going to bring that up. But since we're talking about an equilateral triangle where all three angles are equal, it might be nice to know what the sum of the angles in a triangle are. If we added up all the angles in a triangle, what would we get? Okay. I'll just go ahead and give you that one then. It's 180 degrees. Every time we add up the angles inside a triangle, we get 180 degrees. What that means is every angle inside the equilateral triangle has a measure of 60 degrees. So in an equilateral triangle, the three angles together add up to 180, and each one of them has a measure of 60 degrees. The next type of triangle we're going to talk about is isosceles. In an isosceles triangle, at least two sides are equal. At least, really important. We saw the difference between at least and exactly when we did binomial probability, and at least comes up again here. At least two sides are equal, and in this particular triangle, it would be those two. And so if I have at least two sides equal, I have an isosceles triangle. Up next, we have a scalene triangle. And in a scalene triangle, no sides are the same length, no angles are equal. So essentially what we've got here is we're talking about the side length of triangles. If three sides are equal, it's equilateral. If at least two sides are equal, it's isosceles, and then the only other choice is to have no sides equal. Down on the bottom half of this, we focus in more on angle measures. And the first one we look at is a right triangle. A right triangle has one of the angles measures 90 degrees. Would it be possible to have two angles measure 90 degrees? I'm not sure what you mean, Nicole. Says, oh, Lorraine says no. Why not? And this might not be the easiest thing to put into words, but there are a couple different ways you could go here. And you could give me an instruction and I'll follow it. Excellent, Lorraine. I like that very much. If I have one angle 90 degrees and another one 90 degrees, I'm already at 180. I don't have any degrees left for the third angle. There's nothing left. I can't do it. And then if you were to try to draw it, if you were to try to draw a triangle with a 90-degree angle over here and a 90-degree angle over here, well, the problem is now it can't be a triangle. It's going to have at least four sides. We don't know what's going to happen on the rest. I mean, we could finish it off as a rectangle, or we could, finish it off as something else. But the kicker is we can't have two 90-degree angles because that won't work. In acute triangle, all of the angles measure less than 90 degrees. So in an acute triangle, all of the angles, whatever the measures are less than 90 degrees. And then finally, an obtuse triangle. And in an obtuse triangle, one of the angles measures more than 90 degrees. Here it's this one. It goes beyond 90 degrees. And we couldn't have more than one of those because then again, we'd be bigger than 180. If I had a 91 and a 91, I'm already at 182, which is no good. And I haven't even included the third angle yet. So we can only have one angle that's greater than 90 degrees. Any questions about those definitions before I have you do another true-false setup where we answer some true-false questions about triangles? All right. Same as last time, we have two true-false questions. I'm going to set up a poll just like it did before. Every equilateral triangle is isosceles, and all acute triangles are equilateral. Our approach here is the same as it was before. We're looking for a counterexample. If I can find a counterexample, then I know it's false. If I can't, then maybe in the process of finding that counterexample, I convince myself, oh yeah, based on the definitions, this must be true. That's sort of our approach here. And because of that, and because maybe A lot of those definitions and properties of triangles are new to you. I can give you a little time here. You might need to look back and forth a couple times to sort of make sure, okay, is that really the definition? And that's perfectly fine. So in each case, we're looking for a counterexample, and if we can find it, we can say false. And if we sort of, in the process of looking for that counterexample, convince ourselves that it's true, then that's excellent. That's a fantastic approach. Let's go another 30 seconds, and then we'll talk through these. Let's see. Okay, pretty strong agreement, but spread around again. I do think these true false questions present some challenges. So if you're having trouble with them, that's okay. I want you to ask questions if you're not sure how we arrived at the answer we arrived at. And make sure you get really familiar with these definitions for each of the polygons that we work on. First one says every equilateral triangle is isosceles. Okay, so my approach here is to try to find a counterexample. So I'm going to try to draw an equilateral triangle that is not isosceles and see if that works. So I draw an equilateral triangle. That means all three sides are equal. Well, to be isosceles, what isosceles means is at least two sides are equal. Well, here I have at least two sides are equal. So yeah, that's isosceles. Let me try this again. Let me draw a bigger triangle maybe. Got to be equilateral because that's what the problem said. All equilateral triangles are isosceles. And to be isosceles, you've got to have at least two sides the same length. And that one, you know what? Every time I draw an equilateral triangle, it's going to have three sides the same length. So it has to be isosceles. It's going to have at least two sides the same length. So every equilateral triangle I draw is going to be isosceles. This one's true. All acute triangles are equilateral. So could I draw an acute triangle? All the angles are less than 90 degrees. That's not equilateral because I'm looking for a counterexample. All acute triangles are, well, that's less than 90. These are less than 90. They're pretty close to 90, but they're less. There's a acute triangle. All the angles are less than 90. It's not equilateral. All three sides are not the same length. So here is my counterexample, and I can say that this is false. There's other ways you could draw that. There's other ways you could come to that conclusion, but looking for a counterexample is a great way to go. Let me know if you have any questions on there before we talk about another idea related to triangles. All right. The triangle inequality. And this is something that in a classroom setting with kids, I might let them try it with rulers and string and just see what happens. For us, we'll just talk through it. In order for a triangle to be drawn, the sum of any two sides must be larger than the measure of the third side. So first, let's digest that a little bit. The sum of any two sides must be larger than the third side. What this really says is if I add up the two small ones, it has to be bigger than the other one, than the biggest one. For example, if I try to draw a triangle with side lengths 2, 4, and 11. Now, right out of the gate, according to the triangle inequality, I can't do this because these two, when added together, has to be greater than this other one. 2 plus 4 being 6 has to be bigger than 11, or I can't make a triangle out of this. If we were to try it, and you could absolutely do this with, like I said, with a classroom of kids would be great with string and rulers and a whole thing. But for us, if we try to draw it, if I say, okay, well, I've got this side of 2, I've got this side of 11, and if I try to make a triangle out of this, the 4 isn't long enough to get there. It won't work. You might be thinking, yeah, well, you drew that in a way that would make it happen like that. All right, well, we'll start out with our 4 over here, and we'll put our 2 right here, and then if I connect the 11, you know what? It's not going to make a triangle. And even if I pulled it back a little bit, so okay, you've got that 4 right there, and let's say you put the 2 like right here straight down. Well, then the 11, I couldn't make a triangle with lengths 2, 4, and 11. I've got a triangle with whatever that little length right there is, but the lengths are not 2, 4, and 11. I can't make a triangle out of those. The triangle inequality says in order to draw a triangle, the 2 small sides have to add up to be bigger than the other side. We started out talking about polygons today, and now I want to talk about the sum of the interior angles of a regular polygon. Regular being a really important word for us here. Regular. What regular means is that all the side lengths are the same and all the angle measures are the same. We've looked at one of those so far, and that was the equilateral triangle, was a regular polygon. That would be an example of a regular polygon. Another example of a regular polygon would be a square, because all the sides are the same length, all the angles have the same measure. So those are examples of regular polygons. I want to look at the angle measures though, and what we're talking about here is the sum of the interior angles. If I were to add up all the interior angles. So if we start with the idea of a triangle, and a triangle is going to have 3 sides. Okay, and if we add up the interior angles of a triangle, and I've already talked about the fact that that's going to be 180 degrees. So far, so good. Let me know if anything's not. And then we step it up a little bit to a quadrilateral. Quadrilateral is going to have 4 sides. And you might go with the idea, well, a rectangle has 4 90-degree angles in it. A square has 4 90-degree angles in it. So 4 times 90, this must be 360. And that would be true. But something I want to do, I kind of want to do this with a picture. So if I take a quadrilateral, like this rectangle here, it could be any quadrilateral, and I cut it. I have made 1, 2 triangles inside that quadrilateral. So really, this is just, if I want to add up all the angles that are inside here, if I want to add up these, and then I want to add it to these to get the sum of all the angles, essentially what I've got here is I've got 2 triangles in there. So what I've got here is 2 times 180. The triangle, it just had 1 triangle in it. That was 1 times 180. We didn't write it down that way because we just went with the fact that it was, there's 180 degrees when we add them up. But 1 times 180 gave me the sum of the angles inside a triangle. And 2 times 180 gave me the sum of the angles inside a quadrilateral. We'll take this one step further and we'll go to a pentagon. It has 5 sides. I don't know what the sum of a pentagon is, but you know what? If I draw one, do my best to try to draw a regular pentagon here. It's not going to be the best, but it's not terrible. Okay. The way that I figured out the angles of that rectangle is by cutting it into triangles. I'm going to do the same thing here. I'm going to cut this into triangles. And I have one triangle over here. I have a second triangle in the middle. And I have a third triangle over here. So if I wanted to add up all the angles inside that pentagon, now I have 3 triangles. So it's 3 times 180. And I don't know what 3 times 180 is, but I can multiply that and get 540. So the sum of the angles inside a regular pentagon would be 540. This is great, but if we had like a 12-sided figure, I don't want to try to draw that. I don't want to try to cut it into triangles. Instead, what I want is a formula here. I want to come up with a formula for if I have n sides of my polygon, what is the sum of the angles going to be? I want you to take a minute and look at what we have here so far and see if you recognize a pattern of how to figure out how many times we need to multiply by 180 to get the sum of the angles inside a figure. And I guess what I'm asking you for is, what would have to go right here that we would multiply by 180 to figure out the sum of the angle inside any parallelogram, or excuse me, polygon? That's excellent, Lorraine. So, and I maybe could have steered you a little bit more, but Lorraine got it. It was excellent. If we look at this, when I had 3 sides, I multiplied 1 times 180. When I had 4 sides, I multiplied 2 times 180. When I had 5 sides, I multiplied 3 times 180. So however many sides I have, if we subtract 2, that'll give us the number that we want to multiply by 180. So if I'm going to have n sides, then I'm going to multiply n minus 2 times 180. And that is how I'm going to find the sum of the measures of the interior angles of a regular polygon, is with this formula right here, where n is the number of sides, it's n minus 2 multiplied by 180. And it's essentially how many triangles would we get if we chopped it up. Other questions on this? Before we look at a problem that involves this formula, one thing I will say, if you're thinking, there's no way in the world I would have figured out that formula, that's perfectly fine. I wanted to sort of build it and develop it with you rather than just telling you what it is. The types of problems we see with this are not overly challenging. Building the formula is the challenging part. Now that we've got the formula, the problems I don't think will give you too much trouble. Let's take a look at one. What is the measure of each interior angle of a regular hexagon? So here this question is saying, what is the measure of each interior angle of a regular hexagon? So if I were to draw a hexagon, and a lot of pressure. Let's see, if I were to draw a regular hexagon, not terrible. What we want to know here is, what would I get if I added up all those? And then I don't want to know the sum. What I want to know is, what's the measure of each? So just this one right here, what would the measure of that be? And here's how we'd go about answering it. Well, I know the sum of the interior angles is n minus 2 times 180. Because I know this is a hexagon, I know it has 6 sides. So that'll be 6 minus 2 times 180. If I want to simplify this, we do what's in parentheses first. So that's 4 times 180. So we can go ahead and multiply. 4 times 180 is 720. Kind of feels like I ought to be done. I had a formula, I used it, 720. But 720 is the sum of all of those interior angles. Then I have to realize, okay, well, here I'm working with a hexagon. So that means 6 sides and 6 angles. So if I want to know the measure of each one, I need to take that 720 and divide it by 6. And find out that each angle has a measure of 120 degrees. So in a regular hexagon where all the sides are the same length, all the angles have the same measure, if I want to know the measure of each one of those angles, I can find that by first finding out the sum of all the angles, and then since there's 6 of them, divide by 6 to get the measure of each one. Do you have questions on that before I have you try one? All right, not a lot of questions today. We're doing great. Here goes. What is the measure of each interior angle of a regular nine-gon? And I could have used nonagon there, but I wanted to make sure you knew how many sides there were. So what is the measure of each interior angle of a regular nine-gon? I'm going to set up a poll for this and give you a chance to try it. The first calculation we've done in a couple of days, so I'll give you a little time on this. We've been so focused on definitions, there haven't been a whole lot of calculation type problems. We'll go another 30 seconds and then talk through this one together. Let's see where we are. All right, unanimous, outstanding. I didn't think this would be a hard one for you, and I'm glad that's how it turned out. So I'm not going to try to draw a 9-sided figure that's regular because I'm positive that that would be beyond my artistic abilities. But if I want to know the measure of each interior angle of a regular 9-gon, first thing I'll find is the sum of the interior angles, and I know that's going to be n minus 2 times 180. In this particular case, it's a 9-sided figure, so n is 9, so that's going to be 9 minus 2 times 180, or 7 times 180. And when I multiply those together, I'll figure out what all the angles are added together. That's 1,260 degrees. But since I have 9 angles in my figure, I need to take that 1,260 and divide by 9, and I end up with 140 degrees. And so if we have a regular 9-gon, we end up with an angle measure of 140 degrees. And I told you I wouldn't draw one, but we do have one to look at here, this nonagon right there, that we can see that each one of those angles has a measure of 140 degrees. Any questions about what we did there on that one? Finding the measure of each interior angle by using this formula, n minus 2 times 180. Really, it's how many triangles are there inside? If we chop it up, there would be 7 triangles. That makes 1,260 degrees. So each angle must be 140. That's sort of what we're doing in a problem like that.